All right. Let's talk about a little thing called implicit differentiation. With implicit differentiation, let's say we've got y is some function of x. However, we may not be able to say how that function does work. And matter of fact, this works even if it's not necessarily a function of x, but let's just say that there's some y out there that we can't explicitly say, usually we can say y equals x squared, whatever. But in this case, not so much. We can't do that. Okay? Well, what I want to talk about is differentiating, which I meant to mention that. I mentioned differentiate, that word. That's just another form of derivative, the term for derivative. But differentiate y to the 8th power with respect to x. Let's talk about that. So y is something in terms of x, and then I'm going to 8th power that. So I've got a pretty complex deal because, like I said, if I can't say what exactly easily y equals in terms of x, and then I'm going to 8th power that, I might have something that is pretty complicated. Maybe not so much, but they do typically turn out to be something complicated, is why we're going to talk about this. So, in other words, what I want to do, I can't explicitly get y equals, and so what I'm going to do is do an implicit differentiation, and see what happens. So in other words, here's another way I can. In other words, here's what I'm going to do. I'm going to try to get the d dx of y to the 8th. Wouldn't that be another way to say that? The derivative with respect to x of y to the 8th power, where y to the 8th power, whatever y is. Okay? Here's the thing. Well, it's easy enough to see there one derivative I'm going to have to do. What is one thing I'm going to have to do to this? Power rule. I've got y to the 8th, so I definitely need to do the power rule. What would the power rule give me? Bring down the power, then do what? Subtract 1 from the power. However, there's more to it, because what we're saying is this y, it is something in terms of x. We can't really get it, or it's not really an easy thing to get, but there is something in terms of x. So y is something in terms of x. Does that remind you? In other words, there's something inside here. It's not easy to find, but there is something inside as far as y goes. You see what I'm saying? So what else do I have to do? Does that remind you of the chain rule? By the chain rule, what I have to do is also think about, well, y, the inside part here, that I don't know what exactly it is, I've got to somehow document that. And so what I have to do is, well, I have to say, well, I need to also do the derivative of y with respect to x by the chain rule. I need to have that, like I said, documented or somewhere down there. So here's cut to the chase here, what this means. If I'm differentiating with respect to x, and I don't know what y is in terms of x, what I have to add is I have to add this piece right here. I have to say there's also a dy dx that goes along with, the power rule or whatever it is you're using, trig function derivative. But if I'm differentiating with respect to x, a y, I have to add this dy dx notation is the way we usually document it. We'll write it down. Okay? So here's another. So what would the d dx of 4 y to the 6th be? Doing the derivative with respect to x of 4y to the 6th. Same thing, isn't it? Power rule. Power rule would give me what? 6 times 4 would be 24, y to the 5th. But since I'm doing the derivative with respect to x of something that involves y, I've got to add that dy dx. And so that's what really this implicit differentiation will do, is we'll have some dy dx's tacked onto the end of these things we do the derivatives of. Is that okay? Now, what if, note that if I do the d dx of, say, x to the 3rd plus 5x plus 4, okay, if I'm just doing the d dx of that, what do I get? Well, this, I'm doing the derivative with respect to x, and these are x's. So those are just straightforward derivatives. The derivative of that's 3x squared. The derivative of that is plus 5. The derivative of that is 0. Yeah, that's just the same old thing we were doing. We're doing the derivative with respect to x, so we just get 3x squared plus 5. In other words, we don't need dy dx tacked onto multiplied. With me on that? Yeah, if you think about it, yeah, it'd be dx dx, which is 1. You're doing the derivative of x with respect to x, so yeah. Yes. Okay? All right, now, what happens when I get something like this? What about the d dx of 8x cubed y to the 4th? 8x cubed y to the 4th. What do you see happening on that? Well, hopefully you see a product. And so when you see a product, what are you thinking? Product rule. Okay? Got to use a product rule here. That can sneak up on you at any time. Anytime you have a product, two things multiplied together, which I do, let's just say it's 8x cubed and it's y to the 4th, multiplied together, that's, you're going to have to use a product rule. So product rule, what do? We do the first times the derivative of the second. So let's just say it's d dx, I got to do the d dx of y to the 4th. Then I have to do the second times then the d dx, the derivative of 8x cubed. Okay, and so what does that amount to? Well, it's 8x cubed times what's the d dx of y to the 4th. It's just what we were talking about. We're doing the derivative with respect to x of a y. So we've got to do the power rule, which would be 4y cubed. But what else do I need there? Since it's a y, doing the respect to x, I've got to do dy dx with that. With me okay? Then over here I'll have y to the 4th, the d dx. Now that's just an x expression, doing the derivative with respect to x, so that one's just straightforward, just be 24x squared. So clean that up, 32x cubed y cubed, dy dx, and then 24, let's say x squared y to the 4th. Question or concern? Does that make sense? Is this okay? All right, well, why talk about that? Well, like I said, we're going to get into some of these equations. For example, x to the 3rd plus y to the 3rd equals 15xy. We're going to want to talk about the derivatives of this. Turns out this equation, if you graph it, it winds up looking it's got a little curve in it there, loop-de-loop, okay? Reason I put that out, I mean, we're not having to graph these, but calculators do some of these, and but we're not going to have to graph them right now. But the point is here, do we have tangent lines here? Do I have tangent lines? Can I draw a tangent line here? Just about anywhere, yeah. Got horizontal ones, I've got angled ones, but I have tangent lines. Therefore, I have slopes of the tangent lines. And what are slopes of the tangent lines equivalent to? Well, in this setup, it's y prime, right? Yeah, how am I going to find the derivative here? I can't do it the way we were doing it because, how can I solve that for y? Can I solve that for y? Not very easily. The reason is, I mean, if it was just y cubed, x cubed plus y cubed equals 15x, the y over here and the y over here kind of throws a wrench in the works. It's not going to be easy to get y equals like we were having before. In other words, we can't get it explicitly in terms of y. Y in terms of x, I should say. So we're going to need a different way to get y prime, also known as dy dx, and that's where implicit differentiation comes in, which is tied in with what we have right here. I'll do this one, save that one for later, because that one's got a few things with it. Let's start a little easier and build our way up to that one. Okay? All right. Let's start with x squared plus y squared equals 25. X squared plus y squared equals 25. Let's find dy dx, or the derivative, also known as the derivative of y prime. But we're going to call it dy dx for various reasons here right now. Okay? Here's what I'm going to do. Implicit differentiation, what you do, we're going to use implicit differentiation here. And here's what you do. Step one of implicit differentiation is take the d dx of both sides. In other words, take the derivative of both sides with respect to x. We're trying to find dy dx, okay? So I'm going to d dx. I'll write it all out here this first time. So essentially what I'm doing, yeah, I'm doing the same thing to both sides, right? What you do to one side, you do to the other side. Usually works out. d dx both sides. Okay? Well, this one's nice because this side is just a sum, so I can just do the d dx of x squared plus the d dx of y squared. It's just a sum, so there's no product rule or any special thing I have to do with it. Just do the derivative with respect to x of both of those. And then on the right, it's even nicer because I'm doing the derivative of a constant. So what's the d dx over here? 0. Okay? So this is what we were just talking about. We're doing the d dx of x squared. It's just an x, so what is it? 2x is all I've got there. However, on this one, you got 2y, but since it's a y and I'm doing the derivative with respect to x, what else do I need? I need a dy dx. And again, it's because of that chain rule thing. Y is something in terms of x. I don't know what it is. Later we'll talk about it, but usually we cannot find it very easily. And so we just represent it, that part of the chain rule by dy dx, the derivative of y with respect to x. Okay. All right, now what are we trying to find? Dy dx. Do you see here now? I can do that. Can I get dy dx now by just solving this like an equation? But I'm going to solve for, get dy dx on a side by itself. How would I do that? Wouldn't I need to subtract the 2x? So now let's solve for dy dx. So wouldn't I subtract the 2x, both sides, so I get 2y dy dx equals negative 2x, right? Because that'll go away now. Then what? Divide off the 2y. And so, there you go. Dy dx equals minus, the 2's cancel, so it'll be minus x over y. Look okay? All right. Let's add another part here to this. Let's say, now, do you know anything about this equation? It's a circle, yeah. That is a circle centered at 0, 0. And what does this tell me? Isn't the square root of that the radius? Yeah, this is a circle, radius 5, centered at 0, 0. You don't have to know what the graph looks like, but just FYI. But again, the point is of this, circles have tangent lines, don't they? All right, so let's find part 2 here. Find the equation of the tangent line. At 3, 4. Find the equation of the tangent line at 3, 4. Well, what's the slope of the tangent line? Well, it's the derivative. We've been writing it y prime, but now we're using the dy dx. Same thing, isn't it? The slope of the tangent line is dy dx. Well, here's dy dx. Negative x over y. And so my slope is going to be what? Well, don't I have x and y to plug in? The x is 3, the y is 4. Slope's negative 3/4. With me? It gives me x and y here. Sometimes you might have to find y if you're given x or vice versa. But in this case, it gave me both the x and the y. So yeah, on these implicit ones, you know, usually on the derivative, we just had x to plug into to get the slope. But now we've got x, usually going to have x and y to use when we find our slope. And then the equation of the tangent line, well, it's y equals mx plus b. Now we know m, it's negative 3/4. B, well, we've got to find it. However we want to. X is 3, y is 4. Same thing. It's negative 9/4 over here, so add the 9/4. Whoops. Let's see, what is that? 4, and that's, well, be 16/4 plus be 25/4. And so my equation would be negative 3/4 x plus 25/4. Okay? So really, once you find the dy dx, everything else is just the same. Except just plug in the numbers and then get your... Okay?